Now, it is time to start with the first plenary talk by a distinguished speaker, Professor Thomas Ertl, who is the head of the Visualization Research Center, Vice Rector for Research and Advanced Graduate Education, University of Stuttgart, Germany. I would request Ms. Nitika to please give a floral welcome to our honored speaker. I would request Ms. Chandramani to please present a bouquet of flowers to Professor Shantanu Chaudhary, who is the chair of this session. Sir, please take your position on the dais. Now, I would request Professor Shantanu Chaudhary to please introduce our honored speaker. So you have it?
Yes. Let me welcome you to the first technical session of the plenary lecture by Professor Thomas Ertl from University of Stuttgart, Germany. We are really thankful to Professor Ertl for taking the journey and coming here to Pilani for this talk. And it's a great pleasure introducing him to this audience. Professor Thomas Ertl received a MSc in computer science from the University of Colorado at Boulder and a PhD in theoretical astrophysics from the University of Tübingen. Since 1999, he's a full professor of computer science at the University of Stuttgart, now leading the Visualization and Interactive Systems Institute and the Visualization Research Center at the University of Stuttgart. Currently, he serves as Vice President of Research of the university. His research interests include visualization, computer graphics, and human-computer interaction in general, with a focus on volume rendering, flow and particle visualization, parallel and hardware-accelerated graphics, large data sets, and interactive steering, visual analytics of text collections and social media, user interfaces, and navigation systems for the blind. He received the Outstanding Technical Contribution Award and the Distinguished Career Award of the Eurographics Association and the Technical Achievement Award of IEEE Visualization and Graphics Technical Committee. In 2007, he was elected as a member of the Heidelberg Academy of Sciences and Humanities. He received honorary doctorates from the Vienna University of Technology in 2011 and from the University of Magdeburg in 2014. I would like to call upon Professor Thomas Ertl, who will be talking on interactive visualization, a key discipline for big data analysis.
Yeah. Good morning, everybody. Thank you very much for this kind introduction, and thanks to the organizers for inviting me to this wonderful place. Actually, it's my first visit to India, and I'm really excited to be here. Also, it's only going to be a very short visit, but the impressions from half a day in Delhi and getting here by car to Pilani was already a very rich experience, and so I'm looking forward to a few more days. So I want to talk about visualization. This is my key research field, and actually I want to advertise a little bit visualization as a field, because my impression is that researchers from India are not that broadly present in that field if I go to our international conference, and I really want to encourage you to consider this field as a domain of research which is sort of at the crossroads of computer graphics, IHCI, and high-performance computing. So before I start with the content, I want to give you a little, things seem to be frozen, I'm sorry. Okay, I want to give you a short impression where I come from. So this is a map of Germany, and you see Stuttgart here in the southwest corner. Stuttgart is the capital of the state of Baden-Württemberg. Compared to mega cities in India, it's a rather small city, but with more than 500,000, it's one of the biggest cities in Germany. It's in Europe's leading center of high-tech manufacturing, and you see some of the logos down here from car and manufacturing businesses you might probably be aware of. It's in a very academic center where we have many extra university institutions like Max Planck Institute and Fraunhofer Institute. So it's a very high-profile academic and industrial area. The University of Stuttgart, where I'm now since 1999, has about 28,000 students, and we are very proud to have almost 20% of our student population being from abroad. The university is structured, as you see on the right, in faculties, the traditional European structure, 10 faculties, about 250 professors, 5,000 staff. And it's a university like here with a focus on engineering and science. It's a member of the TU9. This is the group of the leading 9 technical universities in Germany. And you see one number which we are very proud of. So we just recently were number 1 in Germany with amount of funding from the external funding agencies getting to Stuttgart, and this is per professor and year about €250,000 per year. So with this, we are even higher than Aachen and Munich, and so it's very much an engineering focus. And we are especially successful in, you might have heard, there's this German excellence initiative where a lot of funding goes into clusters of excellence about simulation technology. I'm also the vice chair of that in the Advanced Graduate School of Manufacturing. One of those faculties is computer science and electrical engineering, and you see some of the numbers here. I don't want to go into the detail, but I think it's always important if I go somewhere else, if I have visitors, to get sort of a feel what the size of the institutes are. So we have more than 3,000 students, bachelor and masters, just in computer science and electrical engineering. And in computer science, we have many different programs reaching from software technology to media informatics, from business informatics to simulation technology. So one of those institutes, and this is almost the end of this introductory part, is the Institute for Visualization and Interactive Systems, VIS, which I started building up when I got there and which now grew to about 6 professors. And yes, you see down there almost 80 staff in the meantime. So our focus is on visual computing, and for visual computing, we try to bring together fields of graphical interactive systems, which is the name of my chair, human-computer interaction, intelligent systems, visualization, visual computing, and socio-cognitive systems. So this all comes from a sort of visual computing perspective, but it reaches out to many other fields. And as you mentioned initially, sort of since about 10 years, I'm also not only heading this institute within computer science, but a visualization research center, which is a part of the university research centers and a focus of our university. So let me come to the first part of the title of my talk. And this is going to be a very short introduction because you all know those numbers, but we always need to start with a motivational message. So in my understanding, at home we are in the giga age, gigabyte disk, gigaflop CPUs, gigabit Ethernet. If you are more advanced, I think we are all in the tera age. We have terabyte rates in our institutes. We have teraflops, graphical processing units in our desktops. And today's peak, I would say, is the peta era. So you see a picture here of one of the high-performance computing systems in Stuttgart. HPC has 3 top-tier institutes in Germany, in Jülich, Munich, and Stuttgart, and they take turns who gets the fastest system. So we just got an upgrade, and I think at the moment Stuttgart is at the top with a couple of petaflops. But also you look at data collected from sensors. This is in the petabytes per year, like for example in CERN, in physics instruments, or if you look at data, Facebook photos, or digital events, everything in the peta range. Well, we need to get used to the other Greek standards like exa, zeta, and iota. I've heard about zeta, and iota is quite new to many of us. So it's 10 to the 18th, 10 to the 21st, and 10 to the 24th. I think it relates to the digital information which is captured, replicated, created, and there are numbers out there that by 2020 it will grow to something like 40 zettabytes. This is where we need that zetta for. And interestingly, only 5% of this information will be structured so that our standard computer science techniques are able to work with that. And it, of course, appeals to the couple of the V's of the big data challenge, whether it's velocity, volume, variety, and veracity. So how does visualization come into play? This is sort of a cartoon of visual perception. There's a guess by people who know that better than I am that somehow the information stored and processed by humans is about a petabyte in an entire lifetime. So this is nicely related that we are almost in the peta area at the moment. We all know that 80% of this information comes through the vision channel because evolution has equipped us well to deal with space, form, color, texture. Vision is certainly the highest bandwidth human-computer interface we have available, and this is due to the large portion of our brain you all know is related to vision and its related functions. I read a study recently sort of where people try to guess what data rate is inflicting on us. That was for the US, so that's maybe not true everywhere, but there's a guess that about 30 gigabytes per day impinge on us as multimedia people. Yeah? This is less than 1% text, and there's a claim that 50% of that is already interactive, which I doubt a little. Maybe that's a more special focus, but still think of all this information approaching us. And as a computer graphics person, I have to say, all this information streams to us with displays like this, which is maybe a megapixel or 2, if it comes good. So, of course, we need to improve displays technology, and I will show you later. We built a system in Stuttgart, which is a 100 megapixel display wall, a stereo display wall, where you can see sort of on 6 meters width, you can have the same resolution as on your display, almost, yeah? Which enables you really with new ways of interacting with data. So I think it's obvious visualization plays a significant role in analyzing big data, but it's too much information out there just to look at it. So there are two keywords which I think are in the core of visualization. Interaction and abstraction are the both fundamental techniques to deal with huge data sets. So since not all of you are from visualization, I have put in 2 slides to lay the ground what this area is. Of course, you all know what the verb means. In general form, a mental image makes visible, and you see from images on the side that human mankind has done this for thousands of years. And even in the focus of a scientific understanding of visualization, a graphic depiction of abstract data, like you see here in Leonardo da Vinci's drawings, or below, this is one of the first stream flow visualizations of wind patterns over the Atlantic. This dates back centuries. But I think the problem came when numerical computing got started in the 60s, 70s, 80s. There's this famous saying of Richard Hemming, the purpose of computing is insight, not numbers. And therefore, in the early 80s, people found out that the traditional pen plotting techniques were just not appropriate for visualizing the huge data sets resulting from simulations. Back then, supercomputer simulations, computational fluid dynamics, physics, etc., but also sensor measurements, if you think of medical imaging, which provides all this data. So around in 1987, a famous report came out by the National Science Foundation, which we now in our field think as the birthplace or the birth date of visualization as a scientific field. And this report said visualization is the method of computing. It transforms the symbolic into the geometric. This is the mapping, enabling researchers to observe the simulation and computations, and visualization offers a method for seeing the unseen. And of course, we do that by colorful, interactive raster graphics, as you see in this image of the site, where many types of flow visualization are involved. So since this was 87, we are almost 30 years now in the development of a young science. So nowadays, we distinguish 3 areas. Scientific visualization doesn't mean that the other stuff is not scientific. It means that the data comes from scientific applications like in engineering, medical imaging, as you see here on the site, typically data which has a spatial relation. So a physicist would say a field, yeah, related to X, Y, Z, or time, particles, maybe with underlying physics. Then 10 years later, a field started which is nowadays called information visualization, which deals with data from networks, databases, business, web applications. Typically data which is non-spatial, which is maybe high-dimensional or multivariate. And since about 10 years, a new term and a new subfield came into existence, which is called visual analytics. The idea is that you combine highly interactive visual interfaces together with advanced data mining, machine learning algorithms to form sort of an exploration tool which addresses big data from interaction, visualization, and data analysis technology. And you see here a traditional visualization pipeline like we use it to teach visualization. So traditionally, this was a one-way road going from data here from sensors, then it's filtered, and then the visual mapping, which maps the abstract data to a geometrical or graphical representation, and then you render it with the help of computer graphics technology. Now, in modern times, visual analytics means that the user is involved in all of those stages here, that you have semi-automatic and automatic processing steps in between, like machine learning or interactive classifier training, and that you also try to take provenance data of the entire process in order to make the process of visualization and data exploration understandable. So my group in Stuttgart tries to cover scientific visualization. That's where I come from. I used to be an astrophysicist, and visual analytics, the new fields, in quite some breadth. So my group is 5 postdocs and at the moment 17 PhDs. And we try to do research in all those areas which are listed here. So simulation, flow, porous media, magnetic fields. We look at particle data, which comes from molecular dynamics or systems biology. We do high-performance visualization, where trends are that you visualize in the high-performance systems and do a so-called in-situ visualization, because the bandwidth of the systems is not enough to get all raw data out of the system, so you need to process it before you get it out. And more recently, we work in sort of visual analytics, looking at text. We have Twitter analysis, digital humanities, scientometrics. I will talk about that in detail later. Visual queries, and also much more important now to understand how visualization works in the human, which are the basic cognitive and perceptive aspects we have to take care of in order to make visualization successful. And down here you see sort of the technology study, our large display, where we have sort of 10 of the 4K projectors lined up in a system where you see all of those, each of those projectors needs 4 VGA or HDMI in. So actually you need to have, for stereo, you have 20 instances of Windows running to generate one image. And you can imagine there is no such single system. So every software we write for that is starting from scratch. So before I go to the details, 2 images which show you just some, we are visualization people, visualizations of some of our projects, that you can appreciate the breadth of the things we are doing. So we start from flow visualization, which you see here with modern numerical techniques, to something like in the systems biology, where we try to understand signal production processes, but also to particle systems. You see here millions of molecules interacting in a physics simulation. In flow, where you try to understand how droplets behave, especially in the diesel injection engine, where sort of you have fuel coming in and going away into thousands of little droplets, and how they actually interact. But also particles are based on laser ablation or types of protein interaction. In the visual analytics, things look a little bit different. It's more information visualization style applications, ranging from interfaces to access pattern databases, as we see here. Twitter analytics for security analysis. This is a system looking at tracks of public transport systems, and the one on the above I will show you in a second. So, concluding this introductory and more sort of overview part, my view on visualization after being in the field now since almost 30 years is I started as a physicist, obviously in scientific visualization, with a focus on interactive visualization of volumes and flows, which requires understanding of flows, features, what is turbulence, what are vortices, stuff like that. But also we understood very, very early in my career that if you want to have interactive visualization, which means you need to generate images with 20 frames per second, then you need very much advanced computing power in order to do all those visualization processes. And so we were a few of the first using graphics hardware as it became available in the early 2000s, to do GPU-based visualization. Later I moved into visual analytics because I'm already interested in the new data types which came with that, whether it's ranging from video data or text data or trajectories of movement patterns. So many of our projects that nowadays involve as well spatial data, like physical fields, but also non-spatial data, where position is sort of only indirectly involved. And so, in my understanding, many challenges to scientific visualization and to visual analytics are quite common. Although some people think they are different fields, I think in my understanding that's really close. They deal with sometimes really big data, with complex simulations, with advanced data analytics. And so in the rest of the talk, I just picked a few examples of our current research, which I want to present to you to show you the breadth of our field. And I picked one example from scientific visualization, solar dynamics, I will show you in a second. And then I picked 3 examples from visual analytics, because my feeling is that the IHCI community, of course, is a little bit closer to the visual analytics domain than to flows and volumes and so on. So let me start with the first example. You see here a solar flare in the video running on the side. This is from a collaboration with the European Space and Technology Center, and they wanted to enhance their visualization capabilities beyond just looking at images. Their research question is, how does the sun generate its magnetic field? How does it produce those flares which you see in the video, which lead to coronal mass injection, which we all know influence our space weather and destroy some of our radio communications. So they ask, how is the solar corona being heated, and how does the sun influence our space weather? So our contributions, which I will show in a few slides, are sort of technically, how can you actually do a volume rendering of such situations, but also, can you help understand what the topology and the physical nature of this actually is? So, as visualization people, we always first have to talk about the data. Where's the data coming from? And then we talk about the techniques which we use to look at them. So this data comes from a satellite which is called Solar Dynamic Observatory. And this has 2 types of instruments on it. One is sort of a classical imaging thing which has different resolutions in different wavelengths. And you see a couple of those images from those detectors here, where you see sunspots and coronal loops and coronal mass injections. And the second instrument is called here an HMI. This measures magnetism. It can measure it's a magnetogram. It measures magnetism on the surface of the sun. And there are images which you actually see here from this magnetometer. If you overlay those images, you see that effects like those solar flares are actually related to the magnetism on the solar system. So what we started out doing is, well, there is only data on the surface, and if you want to do a volume visualization, you need to reconstruct the field into outer space. So you start out with data on the surface, which is a magnetogram, and then you have some boundary conditions with the astrophysicists tell us, and so we reconstruct a 3D velocity field or let's say a magnetic field in the outside. And if you want to render that, this has a couple of implications. What you can do once you reconstructed the field, you can compute field lines, as we know from traditional physics, but you can also overlay this with a volume rendering, which shows you the density and the strength of the magnetic field. And in order to do so, it becomes clear that it's not so trivial. Classical ray tracing would send a ray like this. But if you move to a computational grid, suddenly a straight ray gets a bent ray. So it's not so trivial to bring this to the graphics card in order to do this as an interactive visualization. But once we have it, you can combine this with a technique which I will not explain in detail. It's called line integral convolution, which is a good combination of showing the flow structure by lines, which are actually a vector texture in the direction of the field, and which is overlaid now with the volume, and it's clipped appropriately so that you get a good impression of the structure of the magnetic field. So they were interested in coronal loops. This is one of those things which you see over here. So what we do is actually we try to recompute those coronal loops based on the data we've gotten from the satellite. So what we do then, we are interested in generating images which look or resemble the images which were taken by the satellite in the visible spectrum. So what we do is we invent a so-called plasma flux texture on the surface, and then we propagate this texture out along the magnetic field lines which we reconstructed. And then we get images, and this is our rendered image, which is completely reconstructed from the 3D magnetic field. And this is the original images taken by the satellite. And you see that things are quite close. That means our magnetic reconstruction works well. But now we have not an image, we have a 3D data set. So we actually can change the viewpoint. We can look at this solar flare at the side from a side view and get a better understanding of the three-dimensional complex structure of this magnetic phenomenon looking on the side. What the astrophysicists are even more interested in are the so-called coronal holes. Coronal holes are areas on the sun where there is low X-ray emission, and you see them here lined out. Low X-ray emission means they have open magnetic field lines, and this is where the material from the sun is driven out of the sun's magnetosphere. So those coronal holes release the solar wind, which influences our Earth's space weather. So what they traditionally do in order to find out where those areas are, they take a simple computational approach. You might have thought so. Well, you sample the entire surface of the sun and start lines, particles, try to trace them outside. Some of them will return back to the sun. Some will be found here or confined into loops, and others will escape. So what they actually do is compute a so-called escape map. And you see here a very raw example of such an escape map. Gray means those are rest streamlines. They return. Escape forward means they go out, and the yellowish means streamlines come into. So if you try to compute this, this is a large picture of that. This is a traditional effect, and now you see, well, there are little islands out there, and it's not so clear. Are they alone there? Are they connected? Well, actually, if you try to increase, here this is an inset of this little area. If you increase numerical resolution, you see the little dots here. So it obviously is a numerical effect. It's not so clear, that they are not connected. So at the end of our research, which one of my PhD students did, we actually come up with a topologically correct way of identifying those structures. And then you see that this little structure is connected over here by a very thin corridor. So how do we do that? The mechanism is called an isocline surface. So isocline surfaces consist of all points where a vector field exhibits a given slope. So the dashed lines in this image here are isocline surfaces of level 0. So you see that there are magnetic field lines where they have a 0 slope, and so this is where they intersect the isocline surface. So once you compute those surfaces, you can try to reconstruct which of the particles are sort of returning back, as you see some of them here, which are escaping and which are sort of bound in loops. And instead, there's an explanation, but let me just explain this graphically, that you understand the procedure a little bit. So we compute those zero-slope isocline surfaces. This is, for a concrete example, the green surfaces reach out. Then we reject those surface parts that intersect streamlines which escape, go to the outside. Then we extract the boundary curves from the remaining parts. And then these curves are used as seeds for stream surfaces. So they go back down in order to find this structure. And once we have that and intersect it with the stream surface, with the surface of the sun, you get the skeleton, which we, in addition, improve a little bit by topological considerations, because we know that certain topological criteria like saddle point, and things like that actually have to be fulfilled. So I don't want to go into the detail of that, but at the end you can really identify those regions and cut equivalent holes in there. And then you have such a topological map which is really used in physics. So up to now, there were two views from the physicists. You see here a publication from 2002 where physicists say in some of the unipolar regions, coronal holes may exist of several apparently disconnected components. But there's a conjecture by a guy called Antiochos. He says coronal holes are unique in that every unipolar region on the photosphere can contain at most one coronal hole. Obviously a contradiction. And we found out that this actually depends on how you consider the escape radius. So here we have an escape radius of 2.5 solar radii. Here it's 1.2. And depending on how you interpret this effect, you see that sometimes there are areas which are connected and go from one semipolar surface to the other one. So actually that helped here astrophysicists to get a new understanding of what is possible there, and this is still not fully resolved, but visualization can contribute to understand complex phenomena. So far for the scientific visualization example. Now let me go to something completely different. This reaches now into visual analytics of trajectories. And this is a project we have done together with a utility company, electric utility company in Stuttgart. What they did a couple of years ago, they gave 500 of those electric scooters just for free to the people if they agreed that they would be tracked. So there's a GPS on every device, and the data was collected. And this utility company was interested whether e-mobility would actually find its way into day-to-day life. Would actually people switch from car or from public transport to such e-scooters? So the data set we got, it contains about 150,000 trips, more than 1 million kilometers, almost 100 million measurement points of the data. So what we did is try to come up with a system which lets people explore those 2 years of measurements in an interactive, analytic way. And you see a screenshot of our system here, which I will explain now in a little bit more detail. So the basic concept are so-called lenses. That's an interaction metaphor which you move around. And we start out with the origin lens. And so with the origin lens, all the trajectories starting out from within this lens are highlighted. Then you can have a destination lens. So all the trajectories which end there can be highlighted. And you can have a way-through lens or a waypoint lens, which means every trajectory which goes through there, will be highlighted. And this should be done interactively. And here you see that you can combine those lenses in a Boolean fashion, to have very sophisticated queries. So actually, if you want to find out whether people going through here, which has a steep hill in there, which drains the battery, have a different behavior than the people going down here, which might take longer. So this is the system, and the system is built up with this lens metaphor, different lens types for exploring the trajectory start, which I've showed you, and the Boolean combination. And what you see down here is if you have a data set for 2 years and you want to find quickly windows of half an hour, you need to think of new interaction techniques. And this is what we invented here. There was a nice paper by one of my PhD students, a smooth scroll, where you see on different levels, days, years, months, order, and it's actually based on the graphics projection. So it's a perspective way of manipulating those different layers of hierarchy, which is a very natural way to interact on each of those levels at appropriate technique. So let me give you one example. You see here, is it working? Yeah, you see here a destination lens going over the area of Stuttgart. And you see that there's interactive rates. All the trajectories are at the moment accumulated. And you see on the side, there is a basic statistics provided in a tooltip about average battery drain, about temporal aspects. They look there. And it's a context-sensitive highlighting of all the selectable endpoints for user guidance. And you see that if we had 100 million data points in there, you need really to think as a computer scientist about hierarchical data structures in order to do those things with 20 frames a second. So the next question we asked, well, now we know why people start here and go here. But the question, that people start here. But the question is why? What are they doing? So one of my PhD students, Robert Krüger, had the idea to go a little bit deeper into social media, like Foursquare. This is a social media location service. They have stored a large number of point of interests, I think 30 million. And the information about whether they are visited and what is there is regularly updated by users. So we thought that would deliver additional information on the users. And you see here a map of Stuttgart where those symbols are showing sort of a gas station, a car park, some medical facility. I will get back to that in a second. So what we actually did is we cluster our destination and waypoints. So from 150,000 stop points, we derive 1,200 clusters. And for those clusters, we try to generate a hypothesis, what is there, based on the Foursquare information. So what they give us is a semantic aggregation. You see their icons, which we just use. And for professional other places, it's split up into events, sport, funeral homes, library, and so on. And then if you are interested in government building, it splits up in Capitol building, City Hall, and so on. And at the end, if it's a monument here, you know it's a monument in this certain city. So we try to use this hierarchy to show, to convey visually what the user actually was been doing. In order to do that, we create a hypothesis. So we found out that in our cluster there are 6 locations, and it turns out that 4 of them are restaurants, actually Japanese restaurants, and another one is an Italian restaurant, and this one is a factory. But obviously, we assume that more people actually go to work in the factory than visit the restaurants. So you can use what is called in Foursquare the check-in, how many people are there. And obviously, there are many more people checked in to the factory location than into the restaurant. So you can take this information into account to show why people are there and what they are doing. And at the bottom of our visualization, we have such a little stream graph or a Sankey diagram variation where we show over the day, this is an entire day, what people are doing with their icons. So they start out at home, maybe going out for breakfast. Then later they go to university or they go to work, and later they go home and sort of resume their private life again. And so in order to show you, this is an overview of the entire system. I have a little demo showing here. So we start out with showing the points of interest in Stuttgart. Actually, down here is the university. You see there are various types, and where there's no little icon, just a little number, it was clustered. There are more than one, interesting points. So we start out with a lens showing all the trajectories of the people starting there and where they would eventually go, highlighted by the yellow points. Well, we increase the lens a little bit and look at interesting parts of the city. And in the upper right, you see some additional information. Here, it's the powertrain of the battery for all those users who've taken this path. And we can connect now those lenses and inspect a little bit closer what might have been interested for them to go there. So you see here, this is in Stuttgart West. There are professional institutions, and here we have more shopping available, and you can probably do another lens in order to combine what they really travel. And you see up here, the complementary information about the system of all the users over all those 2 years who had a similar movement pattern in order to improve sort of maybe the situation of charging stations and so on. And in the bottom, you see what people sort of did over the day for this selected user group. So this becomes very sensitive if you drill down too closely, especially I don't have a slide for that. But if we connect it with our Twitter analysis, I can even tell you where the student party was, where they parked their bikes in this context. So this was a use case. And I want to get sort of closer now to text documents, which are now of very great interest to the visual community, visual analytics community. And I have always been interested in scientometrics. So I have been the editor-in-chief of our top IEEE journal, the Transaction Visualization of Computer Graphics, for 4 years. And in those 4 years, I think I've seen about 1,000 submissions. 300 were accepted, and for 1,000 submissions, I at least glanced over approximately 4,000 reviews. So I think I had a very good view of what our field was doing. But still, at the end of those 4-year terms, I was not able to tell you whether animation goes back and modeling increases, or Cyvis wins against visual analytics. So it's very difficult. Also, you have a lot of data to interpret this. And so I was always interested in, can we analyze this much better? And so I started a project with one of my PhD students to look in our scientific data sets. So actually we curated all of our publications of our top conference, IEEE Viz, InfoViz, and VAST. We have digitized everything, metadata, abstracts even, and try to build a system which helps us to understand citations and aggregations. So what you see here is a stream graph. I will explain this in a moment. It's a combination of a temporal behavior over here and a thematic structure of authors and documents in there. So let me look at this in a little bit more detail. So for each of the year, we cluster all the documents. We try to find a topic model, and we cluster this, varying in the number of clusters we want to have. So if you only look at visualization, it's one cluster. If we cluster a little bit more, actually Cyvis and InfoViz and visual analytics separate. Yeah, and you see how things start over the year. So let me start this animation here. So, and now you can move over each of those venues, and you get a word cloud of the most important terms in this year. And what you see on the right is actually the venues which were cited. So we are interested, where does the research come from? So you see here on different levels of granularity. Obviously, here the upper one is the visual analytics. And now we are interested, a large portion of those citations from the knowledge discovery field run into that. And if I stop this for a moment here, you see that the number of citations to knowledge discovery increased even in Cyvis, but in visual analytics, which is on the top, this is the major source of outreach to algorithms of analyzing new data. So you get a very good understanding of what is getting into the field and how it's structured. And in order to do this even a little bit more significant, for each of the year, then we extract the 10 most prolific authors. If I hover over that, I would see the names, how they behaved over the years. So this one was author number 6, in this year, and then he dropped to 10, and then he moved up to 9 again. We have a little line here which shows sort of the average age and the entropy. I will explain on the next slide. And this is very interesting. This is a plot which shows citation count versus trendiness. I will explain on the next slide what that means. So document clustering, I think I've shown you what that means. They are clustered according to thematic similarity. We use spectral clustering because if we partition the similarity graph, and then a hierarchical clustering to show, several you see here on the side that you can cluster in either 2 groups or 3 or 5. And it's very nice that actually our fields segment out by definition. So the word clouds are really descriptive keywords per stream and per year, and they are generated actually from not only the title, but from looking at the paper abstracts, and the difference in term occurrence are actually modeled into the probability. So one example is down here where you see network analysis and knowledge are related to visual analytics in that year. So the cluster of cited venues is on the other side, and this is actually from our DBLP database. I don't know whether you use it. It's a German-based computer science literature database, and we use it to normalize venues, to find the effect of that. And it's also hierarchically clustered so that you can either have one cluster or spread it up into different communities. So what you see down here, we have the average age in blue of a citation. So where's my mouse here? So blue is citation age. So how old is this cited material on average? That tells you something about the development of the field. And the citation entropy. So how diverse is the cited material? And obviously you would hope that it would increase over the years, but that's not always true. And the final view on that is sort of the author and trendiness score. The author score, I don't have a video in order to shorten that up, but I want to point you to the trendiness score. So the trendiness is here on the x-axis, and the assumption is that trend-setting papers have little similar topics related in papers in the past, but lots of similar papers in the future. Because when they are fresh, yeah, this is a vocabulary or notion which is not cited a lot. No one has talked about it. And in the future, it will suddenly, everybody will say, what a great paper. So you actually, yeah, have this here on the trendiness, and it's related to citations. So not always well-cited papers are trendy. You know that from surveys. Surveys are not trendy by that definition, but they are well-cited. But in order to inspect that, this is also an interactive view. So you have a lens again. We use this lens metaphor a lot. And you can get the author names and titles, yeah, what's in there, understand that a little bit more closely. And if you're interested, what is the reasoning about the trendiness? You get on the one column all the papers from the past, and on the other column all the papers which will be citing this in the future. And you can get a very well established or a well-founded knowledge why this might be trendy. I looked at that in close because what is nice about this data set, it's my field. I know this very well, yeah. I can argue and question every single result here as opposed to other data sets where I'm not the expert. Okay. Next example, and this is the one before I close. I wanted to show you that digital humanities is now a very prominent field in Germany. Actually, we just won recently a new center for digital humanities in Stuttgart. So the idea is that computer science helps to let humanities grow by digital or computer science-based methods. And there are a few disciplines of our field which are really obviously close to that. This is computational linguistics. They help to understand texts, but it's also related to visualization in human-computer interfaces. So I want to shortly report on a project called ePoetics. So it's meant in the discussion of the literature scholars, it's called algorithmic criticism, which they use as a term for bringing this technology into their science. It's a collaboration with the new German literature chair and the chair of computer linguistics. And we focus on a very special corpus. It's called the Poetics. It's books about the theory of literature as a science. Yeah? So it's not prosa, it's not a prose. Yeah? It's a theory book on literature science. And they date back to 1600 or 1700, and we've got, I think, 20 of those books. They are books about 100 pages. And it's interesting to try to find out how certain notions and relevant authors evolved over the years. So is Goethe relevant in the 1700s, more relevant than in the 1800s? Is our standing of beauty different over the years? So that's a very interesting text, and it's very difficult also for our colleagues from computer linguistics to deal with those vocabulary in there. So there are visualization challenges to scale from intra to inter-document level to develop smooth interactions for those topics. But there are also a lot of NLP, natural language processing challenges, because this is times text from the 1700s. That's a different vocabulary. And it's very interesting to have such a tight coupling between NLP and visualization. So I show you just a glimpse of the tool we published 2 years ago. It's called a Varifocal Reader. It aligns visual abstraction of the text together with the real text. So you at the same time can read the text and the document structure. And this is what literature scholars actually like, because they distinguish between close reading, they sit on a book and read it, and distant reading, which means they look at the structure of the book. And this is, to my knowledge, one of the first tools which combines both together. So we let them look at chapters, paragraphs, and sentences, and this is how it looks like. And we complement those texts with little visualizations they know, like a bar chart or a word cloud or a line diagram showing different aspects of the text. So this supports linking and brushing. So you click on a word here, this is Homer, and you see how often it appears in the subchapter, and it's highlighted in the real text, and you can search for words, and you have a little line chart to show you the relevance and the link to other authors you looked before, and it's sort of advanced by NLP techniques for sophisticated search technology. So only looking at chapters and subchapters is not helpful. Sorry for that, it's a German text, but I think you understand the notion. So there's a granularity on a logical level also. So you pick certain words like a plant or the mind or language, and suddenly you can group the text where more of the chapters are corresponding to these important words, and then you do a topic segmentation. And you see a little sort of diagrams here where you can help literature scholars to annotate what this word means in this context as compared to the other context. So here's a little video where you see the text on the side. You see that users can navigate either on the full or on the chapter or on the subchapter level. And once you select one of those icons, you get a word cloud characterizing here the chapter or the subchapter, and you have little diagrams showing the relevance of words in this context. So this is what they understand as distant reading. You look at the structure, and at the same time you can make references by doing a close reading to understand this in detail. Final chapter. I have 5 more minutes. I will be finished in time. So what always drives me is the question, why does visualization work and how? And you all know eye tracking has become very popular. I haven't done that 5 years ago, but then we started a group with 2 PhD students, and 2 years later we had the most papers on the Ertl conference, which is the eye tracking conference. So it's a really natural combination of visualization and understanding what the user does. There are 2 aspects. One aspect I'm interested in is how does visualization work? The other aspect I will show you in a second is that eye tracking per se is a source of big data, and you need visualization to understand eye tracking data. Yeah? So there are 2 different aspects. So I think you all know how eye tracking works. I don't want to go into the detail here. The core assumption is the mind-eye hypothesis, that things you have insights are somehow related into what you see. And there are many devices out there, and I don't think that to this community I have to explain the terminology. You know, there's a stimulus, and we look at gaze points and saccades, and we count fixations. And actually what we do, we group fixations in area of interest in order to get a relation between where people look at and what that semantically means where they look at. So eye-tracking visualization started quite some time ago. Trivial things like a heat map here or a scan pass, but those images are very hard to really understand if you go beyond 1 or 2 users. And the typical eye-tracking studies should involve certainly more than 1 user. So we thought long about new techniques, comparing users. So one of the things we published is the PSP, the parallel scan pass technique, where you actually align scan paths relating to different areas of interest on a vertical bar, and then for different users show how they move between different areas of interest, and you can select, that's an interactive system, again you brush and select certain parts of that. More recently we tried to combine sort of these transitions between fixations on such a transition diagram which has a radial shape, and for certain applications this is really helpful. We have just sent another paper on this to Eurovis last week. So, but what I wanted to say that evaluation is also a big data problem per itself. And we found out that if we want to understand visualization, just looking where the user looks at is not enough. So we try to extend this a little bit. So we now, when analyzing visualizations, we collect, besides eye tracking, which is this symbol here, recorded by an eye tracker, we instrument our visualization applications in order to do an interaction log. Where did they click? And we have a microphone turned on and ask them to do a single out study that we understand what insight is generated. And so after the data collection, we need to synchronize eye tracking events, click events, and annotated script of the insight in order to have a more comprehensive understanding what the user does. And the end we do a data analysis, visual analytics approach to understand that. So we have data on what, eye movement, how, interaction, why, thinking aloud. They are collected, and they have then to be annotated and transformed on the different levels. And then the different methods we have for evaluating eye tracking, log analysis, and text analysis is combined together to a quantitative and qualitative behavior of the user. So I show you one slide of this tool which we published last year with the title VA squared, so Visual Analytics for Visual Analytics evaluation. So what is interesting here that you, for one participant, you have such a little visual representation of eye tracking over the different areas of interest on the screen. This little icon, excuse me, this little icon is an insight which we know from the thinking aloud protocol, and this little icon here shows to an event which was generated by the user was operating the system. And it's now interesting if you have more than one user that you try to find and compare similar patterns of users. So we've programmed a pattern selection mechanism where you have one user and another user, and you have such a pattern which you are interested in, you can find it in this huge vast of data for common substrings, and then you can group users, and I think this is the most important thing. Are there certain clubs of users who always behave similarly by doing an interaction with the visual system? And so this shows you the entire prototype here, the main view containing all the participants, the pattern editor, the search options, the result list, and the participant list which is grouped together in a dendrogram. Okay, so last slide to connect this. We applied this tool now to the tool I presented before, the varifocal reader, which we used to do this close and distant reading. And the interesting thing is, we had two user groups. One were our computer science PhD students, and the other were the literature scholars. And it's amazing how different those two groups approach such a system. So while I let the video run, you see the eye tracking and how people move for a certain task where they look at, how they try to find the text in the real system, then they look at the hierarchy. So the interesting insight is computer scientists always start from the structure. They are trained to be hierarchically minded persons. And then once they find something in the structure, they go to the text to certify that there is something. Literature scholars, they are educated by text. So they always start with text, and sometimes they dare to go to the hierarchy and understand the structure. So that is a very interesting experiment, and we continue to see that when we know this, how different users react to different systems, that eventually we might have a user profile. This is a literature scholar. Don't forget about the hierarchy. Show him something else. Okay, so this concludes my talk. I hope I was able to show to you that I think visualization is instrumental in getting insight from really complex data sets. Visualization as a field is really a very dynamic and growing discipline. Last IEEE conference just had record numbers again, more than 1,000 attendees. We need to combine core visualization, and we talked to Dr. Nadal about this. You always have these core questions. Does that work? Is there new insight? But visualization as a technology always reaches out to application. There's no sense of a visualization application without being tuned to an application domain and to an end user. So we try to cover this whole spectrum between application relevance and new insights. And this leads to challenging problems. And whenever I reach into a new field, and you see we do many application fields, it's, again, interesting questions. And for some future trends, I think a tighter integration of interactive visualization and machine learning, this is what we worked on. So we have visual interfaces to support users in training, classifiers. I think quantitative measures. So far visualization was, this is a nice picture, this is an even nicer picture. We need to have more quantitative measures to deal with uncertainty, provenance, and visualization. Big data will be being on the head of our minds for scientific visualization, where we have remote visualization, service visualization as a service. And at the end, I'm interested in the why. I want to move from the what to the why, so visual insight, not only of phenomena, but of causality. And this is going to be a big problem. Thanks for your interest, and I'm ready for questions.
Can I have a few questions? Yeah.
Can you talk, because the air conditioning is very loud, it's hard. Just try to speak to the... If not, I'm come close, and then it's fine.
It's
Just
okay.
to speak up.
My question is related to eye tracking movement,
Yeah.
the last database which you have showed. I just want to ask, did you experiment only for the plain text, or did you use color data or pictures in the data?
Oh, no, this is not only text. So actually, one of my PhD students really tried to understand how visualization works on very elementary graphical depictions. So he investigated bar charts or pie charts or things like that. So given two bar charts, can people find out what is different in one or the other? So actually for reading a bar chart, you could have a typical question, what is the second highest? Yeah? We tried to segment the visual procedure those people do into very elementary steps like reading x-axis, reading y-axis, reading the labels, trying to find the highest, going down and reading the number again. And actually, once you do that, you can really, for such simple visualizations, segment those complex visual tasks of understanding a bar chart into very elementary steps. And we actually try to have a model like you from IHCI, you probably know the KLM model, key level. We try to have a similar model for understanding or predicting task performance for simple, very visualizations. That was not entirely successful, but that's at least one way we try to go. So it's not only text, it's a variety of images. I have another colleague who looks at how people look at videos. Yeah, that's a different story. Yeah.
I would like to go back to the example of the electric motorcycle.
Yeah.
Were there any privacy concerns? I mean, I did not.
Yeah. Okay.
You understood my question.
So of course, so in this situation, it was really special that people agreed when they received the e-scooter that they would be GPS tracked. So in this term, it's a consent that the data can be worked on. We did anonymize the data as much as possible, but of course, if you know where they start, you know that's where they are at home. Yeah. So of course, in this visual analytics application, I'm very much concerned about ethical aspects. And we all know that if you have this database, if you combine it with another database, I did not show you, but I told you for the example of Twitter, I can actually tell you why they went there and whom they met. And of course, I think all the security agencies out there already do that. We should be aware of that. So on one perspective, I think it's good that we as scientists show what's possible. And, you know, I can take political measures, but we try to be as abstract as possible. And if we publish things on our diagram, you cannot conclude anything about an individual person.
The last question, let me just,
Thanks for the fantastic lecture. I'd just like to know whether you have got some data on the percentage of times a literary reader is shifting towards the structure, if at all.
No, we don't have that yet. This is subject to a new user study, because this is something really the literature scholars are interested in, because they argue we don't need structure. We know that by ourselves. Yeah. At the end, I'm very much convinced that this is not true. They don't know structure, and this is why don't they?
They're not trained with that.
They are not trained with that. That's a completely different mindset as a computer scientist who always goes top down. So I think it's also a generation question. When people in these sciences will be used to such tools, they will have a completely different perspective on such things.
What about
I think because of the lack of time, I am just closing the session here itself. You will have opportunity to talk to Professor Ertl during lunch and other breaks.
I will be around all day and even in the evening, so please approach me.
He will be available. So let us thank Professor Ertl for the fantastic talk. And with this, we end this session.
Thank you.
Sure. Would need some water now.
It's on.
Okay, thank you.
I'm really interested in that.
We can go out if you want.
No. Thank you, sir, for all the effort you did put in exploring the horizons of knowledge and imparting it in a very easy and understandable way to us. And thank you, audience, for making this session an interactive one and sharing your valuable ideas. I would request Professor J.P. Mishra to please present a memento to Professor Thomas Ertl. Thank you, sir. Now, we begin with our first technical session, which will be chaired by Professor Sukhendu Das. Professor Sukhendu Das is a professor in the Department of CSE, IHCI Madras. Professor Das did his PhD from IIT Kharagpur in computer vision in the year 1993. He worked as a postdoctoral researcher at the Department of ET and IT, University of Applied Sciences, Pforzheim, Germany from December 2001 till May 2003. He was a Glidden visiting scientist at the Department of CS and SE, University of Western Australia, Perth, Australia, from 2006. He also was awarded the Australian Leadership Award Fellowship at the Department of CS and SE, University of Western Australia. Some of the recently completed and ongoing projects of Professor Das include the project funded by DRDO, titled Localization and Identification of Targets, and by DIT, titled Service-Oriented Architecture and its Implementation for the Linux Kernel, in collaboration with DOS Labs. His research interests include visual perception, computer vision, image intelligence, graphics visualization, biometry, computational science and engineering, analog and digital systems, and soft computing. I would request Ms. Nitika to please present a bouquet of flowers to Professor Sukhendu Das, the chairperson for this session. Now, I would like to request Professor Das to please start the technical session. For the authors, I would just like to inform that every author will be given a maximum of 12 minutes for the presentation, and there will be 3 minutes for the question and answer session. After 10 minutes, a placard will be shown, so please take care of the time limits. Thank you.
Presentation check karana है.